It's time to look at a new concept, and that is the concept of exponents. Now, exponents come about naturally in the course of studying arithmetic. In an arithmetic class, if you are given the problem to take 5 and add it to itself 4 times, you would naturally want to take that addition problem and turn it into a multiplication problem. 5 added to itself 4 times becomes 5 times 4, which we all know to be 20. So the next step would be to wonder, what would you do if you were asked to take 5 and multiply it by itself 4 times? Well, that's where exponents come in. When a number or variable is being multiplied by itself a certain number of times, we write this using exponential notation. With our exponential notation, there are two critical ingredients here. First of all, the 5 is going to be called the base. And in an exponential expression, the base is the only thing that gets multiplied, and it gets multiplied only by itself. A common mistake is for a student to say that 5 to the 4th power is the same thing as 5 times 4, when clearly, if you look at it in the form that it came from, that's just not the case. The 4 is the part that's actually referred to as the exponent. And if you want to see what 5 to the 4th power is, because if you try and do it in your head, 5 times 5 is 25, times 5 again is 125, it kind of gets hard. The easiest way to handle some of these exponents, because the numbers do get big in a hurry, is with the calculator. Now, your calculator will put exponents in a different form. In other words, they look different on the calculator. We have this key right here. It's called the caret key. And the caret key is the key that you use to raise anything to any power. So for 5 to the 4th power, we're going to hit 5 caret 4. And even though it doesn't write the 4 up and smaller like you do on pencil and paper, it still gives you the correct answer of 625. And if you want to verify that, you can go back by hand and say 5 times 5 times 5 times 5. Put it in 4 times, and you can see, of course, that it is the exact same thing. So your caret key is going to be your raise anything to any power key. Alright, now, let's come up with a bit more of a, more formal definition here. When you say that x to the n power, and you're trying to define what that means, that simply means x multiplied by itself, and how many times? Well, n times. So that is the way we typically will define exponential type notation. Now, your exponents are going to have certain rules that come with them, certain rules that they obey. And you're going to find that every textbook has got different names for these rules. Different textbooks break them up into a different number of rules. Some write them as 4 rules, some as 7 rules. But this is the way I typically do it. I usually start off, and we will add to this later, but I start off with 6 rules. And let's just go through those in order. Your first rule is a product rule. With the product rule, we're going to have x to the n power times x to the m power. In other words, same base being raised to 2 different powers and then being multiplied. And we need to see what's going to happen with this. The easiest way to see what's going to happen is with a numerical example. Let's take a x to the 3rd power times x to the 5th power. And remember, the only thing we have to work with right now is the actual definition, or our form of the definition. So let's see what we can do with that. X to the 3rd power means x times itself 3 times. So there that much is. And then we're going to have x times itself 5 times, and that's what the fifth power means. So here's your x to the third, here's your x to the fifth. Clearly what we have here is 1, 2, 3, 4, 5, 6, 7, 8 of them. So that's x to the 8th power. Now how could we more quickly have gone straight from the original to that answer? Well, the answer is add the exponents together, and that's going to be our first rule. X to the n times x to the m is x to the n plus m, and that is in a lot of books called the product rule, so that's what we'll call it here. Now our next example, since we've seen what you do when you multiply like bases, our next example would naturally be, what do you do when you divide like bases? So let's go back to some examples here and see what we can do with that. If I had x to the 7th over x to the 3rd, again, using nothing much more than the definition, x to the 7th is 1, 2, 3, 4, 5, 6, and 7 x's being multiplied. X to the 3rd is 1, 2, 3 x's being multiplied. Now clearly in a division situation like this, I can do some cancellation. In other words, the first x cancels the first one, second cancels second one, third cancels third. I'm left with 1, 2, 3, 4 x's. So, again, we're wondering, how could I have more quickly gotten to that answer? And I believe you can clearly see it would be from subtraction. So our quotient rule says that x to the n over x to the m is x to the n minus m, and that's clearly a quotient type property, and that's commonly called the quotient rule. Now there's another example we need to look at, because there's another possibility of what can occur. Let's say we had a 2 to the 5th over 2 to the 7th. Of course, our base doesn't always have to be an x. This would be 2 times itself 5 times on top, and 2 times itself 7 times on the bottom. And when I go through and cancel, like I did before, you see that I do have 2 left over. 7 minus 5 is 2. But since the power on the bottom was larger to begin with, when all the cancellation is finished, the ones that are left over are going to be left over on the bottom. So this is, once you complete the 2 square, your answer is going to be a 1/4. But the critical point being that the quotient rule says subtract exponents, but the base that's left with its power is going to be left wherever the power was greater to begin with. Alright, so another example or two of this might be worthwhile. Let's say I had an a to the 12th over a to the 3rd. Well, 12 minus 3 is 9. There were more on top to begin with, so this is an a to the 9th. A 3 to the 8th over 3 to the 11th. 11 minus 8 is 3, but there were more on the bottom to begin with, so the power of 3 goes on the bottom. And of course 3 to the 3rd power, 3 times 3 is 9, times 3 is, this is a 1/27. So you have to bear in mind where you had the largest power to begin with, and that's where it will be left behind. Okay. Now our next rule is a zero exponent rule that basically tells us what happens when you raise something to a 0 power. And our last rule, our quotient rule, can actually help us with this a little bit. What would, say, 5 to the 0 power equal? Well, that's the type of question we're looking at. Alright, so stop and think about it. 5 to the 0 power, what should that be? A lot of people will say 5. A lot of people will say 0. Well, let's see what the calculator says. 5 to the power 0 calculator says that is 1. Now, that may seem like a strange answer until you go back to your quotient rule. 5 to the 0 power. How might this 0 come about? Well, that might have been, say, 5 to the 2 minus 2. That's one way to write 0. 2 minus 2 is 0. If this is a result of a quotient rule, then before the rule was used, this was 5 squared over 5 squared. Well, if you just do the arithmetic, that's 25 over 25, and there's where the 1 came from. So anytime you raise something to the 0 power, basically that is a result of a number being divided by itself, which is always 1, with one exception. Let's see. X to the 0 power equals 1, x not equal to 0 itself. Because 0 to the 0 power is going to be, let's see what the calculator has to say about it. I believe it's going to say error. Okay, it says error because 0 to the 0 power is undefined. That's why we got that error message. Now our next rule is a power rule. Power rule tells us something about what happens when something that has already been raised to a power is raised to another power. So let's see what that looks like. Let's say I had a 4 being raised to the 3rd power and then being raised to the 5th power. Well, this 5th power means multiply whatever it is inside the parentheses by itself 5 times. 1, 2, 3, 4, 5. 3rd power means put the 4 in there 3 times each. Here we are, the last 3. Let's take account of what we've got. 3 4s, 6 of them, 9, 12, and finally, this is a 4 to the 15th power. Again, we're looking for a way to get from here to there much more quickly. And the rule is going to say that x to the n power, when you turn around and raise it to the m power, is x to the n times m. And people are always asking, students are always asking how you tell 1 and 4 apart, because it's really easy to get confused. When do I add the exponents? When do I multiply them? Well, let's look at a side-by-side example of when you do each. Alright, so let's take a look at x to the 4th times x to the 3rd versus x to the 4th to the 3rd. Right here you see the base present twice, 2 different powers. This is x to the 7th power. This is when I add them. Base is only here once, 2 powers on the same base. 4 times 3 is 12. X to the 12th is my answer. So basically this is how you tell the difference between when you add exponents and when you multiply them. Let's go on to our next rules. Now, textbooks differ on these next rules as far as how many rules they should be broken into. And here's the way I prefer to do it. I like to make my next rule a rule, well, frankly, that looks a lot like the distributive property. Now, never say that this is the distributive property because it's not, but in a way it looks like it. If you have a quantity, like an x times y being raised to a power, then as long as it's multiplication in here, note this does not work with addition or subtraction, but as long as that's multiplication, you can simply take that power and apply it to both bases. And as a matter of fact, that works just fine in a fraction setting as well. So an x over y to the n power is going to be x to the n over y to the n. So that will work just fine with multiplication or division, but not with addition or subtraction. For example, x plus y to the 3rd power is not x to the 3rd plus y to the 3rd. Does not work with addition. That does not work with subtraction either. Just with multiplication and division. Now we've basically, at this point, been through most of our rules. Let's go back and look at a few more examples where we're actually going to use these rules and see if we can pick up on some of the technicalities and difficulties that come with them. Alright, backing up, sort of going from the top. A w to the 6th times a w to the 5th. Two bases, matching bases, different powers. What's it going to be? Add them, subtract them, multiply them, divide them. What is it? Well, it's w to the 11th. The answer was add the powers. Okay, let's take a k to the 7th over a k to the 2nd. Dividing, what am I going to do? Add the powers, subtract them, multiply them, divide them. This time, subtract. Your answer comes out k to the 5th. Alright, what about an L to the 11th over L to the 13th? Add the powers, subtract them, multiply them, divide them. Well, again, I subtract. 13 minus 11 is 2. Put a 1 on top because nothing will be left. And a second power on the bottom. Alright, now let's take and try one where we're going to use more than one rule at a time. Let's take a negative 3s squared. Alright, you're going to take the 2 and distribute it. Negative 3 times itself will be a positive 9, and s squared is just s squared. Now we need to make a point here with the negatives and positives. If I take a negative 5 and write it these two ways, one with and one without parentheses, and then raise to the second power, what's going to happen? A lot of people will think they're going to come out the same. A lot of people think that the parentheses aren't going to make any difference, but they will. Let's see what difference the calculator says it makes. First time with parentheses. Second time without. As you can see, one comes out negative, one comes out positive. Why? Well, let's take a look at why. This, because the parentheses here imply the negative 5 is being multiplied by itself, that's why you got the positive result. Now here there are no parentheses, so even though there's a negative there, it's not there twice, it's only there once. Alright, so when you're using even powers on negative bases with and without parentheses, watch out very carefully for that sign difference. Now let's look at a couple more examples. Let's look at 5x to the 12th y square over 10x to the 3rd y to the 9th. Alright? Now when you're working with these rules of exponents, one thing to note is that even though they're given to you in a certain order, they do not have to be used in that order. These rules can be used in any order that you want as long as they're used correctly. So I'm going to go over here and do what's convenient for me. 5 over 10 is 1/2. That was the easiest thing for me to do, so I did it first. 12th power over 3rd power. Let's see, 12 minus 3 is 9. There were more on top to begin with, so that's where my answer goes. Next, 9 minus 2 is 7. There was more on the bottom to begin with, so that's where the answer goes. And some might ask, well, what about that 1? Is that really necessary? You can write it, or you can leave it off. That really doesn't make any difference. Alright, so on to the next example. Again, one that pulls together several properties at once. Let's look at x to the 4th, y to the 3rd, over x squared, y to the 5th, and we're going to take the whole thing and raise it to the 2nd power. What should you do first? Well, it really doesn't matter what you do first, but the easiest thing to do first is simplify inside. So let's do that. We'll worry about this 2nd power outside in a minute. 4th power on top, 2nd power on the bottom. When you subtract, x squared is left on top. 3rd power on the top, 5th on the bottom. 5 minus 3 is 2. There was more on the bottom to begin with, so that's where the answer is left. So now the inside is completely simplified. Let's deal with this. Power rule, right? 2 times 2. I'm not adding here. 2 times 2 is an x to the 4th. 2 times 2 is a y to the 4th. And there is your final answer. Now, let's try a couple more. Maybe using a property or two that we've overlooked. Haven't completely used yet. Alright, let's take a 5r to the 3rd s squared, quantity squared, and multiply that by a 5r to the 3rd s to the 4th, and take that to the 0 power. Alright, again, remember what happens with your 0 power. First thing I can immediately see is that this whole thing is going to become a 1. Alright, over here, I'm going to move this second power through. It's going to be a 5 squared. Power to a power, r to the 6th. Power to a power, s to the 4th. All times 1 just gives me 25, r to the 6th, s to the 4th, and we're done. Alright, so there are your basic rules of exponents and an example or two using each. These exponential rules are going to be added to, so just become familiar with these and start getting comfortable with using these, and then we'll add to that shortly.